So we can get the slides up. It's specifically about what is autonomy and what does autonomy mean across this agency. So I'm going to spend the next 25 minutes or so telling you about at least one approach to defining autonomy and to being able to characterize what autonomy. This comes out of work that was done back in 2015 as part of the development of the current set of NASA technology roadmaps. There is a part of the roadmap that is specifically labeled system-level autonomy that's in what's labeled as Tech Area 4, specifically Section 4.5, which was really jointly developed by a number of people, one of whom was Isa Nesnes, which is why I preempted you. And these charts here are a modified version of a set that was originally put together by myself, Isa, and Jeremy Frank, who's also here. So let's get started. Oh, I guess I've got the clicker. What I want to do over the next 25 minutes is go through a number of things. One is provide you context, not just for SMD, not just for science missions, but across the agency, so you can have a better understanding of where NASA may be using or certainly has interest in using autonomy today. Then we'll get into answering specifically the question that you asked, which was about some definitions. And I'll tell you at least the definitions that exist today within the NASA technology roadmap and are actually being talked about in a number of different mission directorates. So I think somewhat consistently about the definitions. I'll talk briefly about some of the technology. Most of today is really focused on trying to have some discussions about technology that is useful or can be useful for future SMD missions. But I'll point out some of the lower level things. Not a tremendous lot of detail. If you're interested, but if you don't know about some of the lower level technologies, but are interested, there are quite a number of people in this room who I know are certainly deeper experts in many of these areas than I am myself. I encourage you to meet them. Briefly talk about research and development that we're currently doing and to sort of wrap up. But to start with, NASA is engaged in a lot of different missions. Mike did a really nice job of outlining some of the things within SMD that we care about. But I want to point out that NASA does many, many things, and so it's many things to many people. Clearly, NASA is engaged in human exploration. There are a number of people here that represent parts of NASA that are deeply engaged in developing and carrying out human missions. A prime example of that is the International Space Station, where you have a number of flight controllers sitting in Houston that spend a lot of time commanding and monitoring and taking care of the vehicle in conjunction with humans, astronauts who are on the space station. They deal with problems that may involve loss of communications, and they have a lot of data to deal with. Lots of software is on board and off board the space station. There's a lot of things that need to be taken care of, and it's a very large enterprise just to manage human exploration in low Earth orbit. Clearly, we've done a lot over the years in terms of robotic exploration. There was some mention about Mars rovers. Here, we have to cope with factors such as the long communication latency, the 20 to 40 minute round trip comm delay that we incur just because of the distance between Earth and Mars. The rovers are capable of some amount of automatic execution as well as some limited amount of autonomy. As Peter pointed out, we do execute missions that have some components that are autonomous. But by and large, they are limited to components or subsystems or limited operations. In aeronautics within NASA, there's a tremendous amount of research and development today of trying to improve aviation in a broad sense. In fact, there is another parallel workshop going on today, in fact, here at Ames, about autonomy in aeronautics. And that really covers a number of different things. Part of it has to do with airspace operations. The national airspace that we fly in on any aircraft today is something that's very complex, but is actually pretty sparse. It's not like we have planes that are, flying within meters of each other, but it's a very difficult management problem because they do fly very fast, and the time to, danger, time to criticality is short. So managing how we operate in the airspace in terms of air traffic at airports, air traffic between airports, air traffic just in the sky is a major problem. Clearly, of course, NASA is interested also in trying to make some of the aircraft that we fly today more autonomous, both in the sense of helping pilots be more autonomous of air traffic control, as well as some of these smaller, or maybe not necessarily smaller, but more autonomous unmanned vehicles, whether these are Predator, Global Hawk class-sized drones, or small-scale drones. Part of the question is, how do we make these systems, which are operating independent of humans, operate in a human world? So all these domains are things that NASA cares about, and if you think about in each one of these, there's certainly different tasks or functions or applications, if you want to use that word, where autonomy can be applied. Across the board, there are a number of different functions here, and I'm not going to try to read this chart here, just to point out that for every single thing that we do, there are different places where we have the potential for applying autonomy. One thing to consider, however, is that for all these applications, there are many different factors that make each and every one different. There are a lot of different constraints in terms of communication time, response time, the amount of resources you might have available on board or off board, the operational environment, the number of assets, interactions, other factors such as regulatory issues, for example, national airspace constraints, planetary protection and deep space, lots of different factors. And what that means is that it's difficult to say, hey, here's my autonomy thing, and I can apply it everywhere, because the reality is that that's not true. The reality is that every single one of these applications is different from another in some way, shape, or form. And that means we have to think a lot about how do we create components that can be mixed and matched, how can we figure out how to, in general sense, improve the operation, the performance of each of these different applications. So back in 2015, NASA did an update to the technology roadmaps. It was a very large year-long effort that involved many, many, many people across the agency. And one of the things that we did is we tried to create a cross-cutting index for a number of technologies. So if you go online and you find NASA technology roadmaps, the first one, which I believe is called TA0, describes a number of cross-cutting things. One of those things is autonomy, and autonomy clearly cross-cuts all of these roadmaps you see listed here, everything from robotics to communications to entry, descent, and landing, modeling, simulation. Across the board, a lot of different areas where autonomy shows up. In particular, if you dive down here, you can see that in some of the roadmaps here, there's some very obvious things. For example, robotics clearly is a place that's really ripe for making systems more independent, more self-reliant. But there are also other areas where maybe you didn't realize that there could be a huge benefit for adding autonomy. In terms of communication and navigation, for example, trying to look at autonomous proximity operations, or perhaps looking over at human exploration destination systems and trying to make habitats smarter. With all that in mind, let me now talk to you a little bit about some of the definitions that we defined during that last road mapping effort. And I'll start off by trying to point out some of the differences between the words autonomy and automation, which in some communities get used interchangeably, but they are quite different. And I put these cartoons up here to be not just a little bit humorous, but the fact is that it really does, I think, capture a lot about what's important in terms of those terms. The first is in terms of autonomy, the desire to be self-directed. And so here you have a guy who's kind of joysticking himself, but the point is he's operating independently. He's being self-reliant, he's making his own decisions. Versus automation, where you can see, a bunch of robots running around, they're following scripts, and then you've got the human just, inside the box here, and it says, in case of emergency, break the glass, which is like, well, when things go wrong, then call the humans in. To a large measure, this is the way that we operate missions today. A lot of our missions, especially you think about Mars rovers, they're operated with command sequences. We generate a very carefully validated, scripted set of commands. We uplink that to the spacecraft. The rover executes that, and in case of emergency, break the glass, call the human in. That's something that we are doing today. It's a big distinction between autonomy and automation. Now, if you want to get into very specific definitions of what these mean, you could look at the dictionary. Autonomy is defined in Webster as the state of existing or acting separately from others. So, you have the ability to go out and do something independent of others, you're autonomous. Within the technology roadmaps, our definition is that autonomy is the capacity of a system to achieve goals while operating independently of external control. So that's a capability, it's a capacity. It's something that the system's able to do. It doesn't describe a technology thing that you can just buy off the shelf, but it's really a characteristic of the system, that it is autonomous. It's able to function independently. Along those lines, I want to point out that autonomy is a relative term. You can only be autonomous if you think about autonomous from who or from what and when. And I pointed out that both humans and systems of all kinds of things, robots, spacecraft, habitats, can function autonomously. That's an important part. If you look at the agency here, we care not just about making spacecraft more autonomous, we also care about human crews as they go into deeper space being more autonomous, more independent of Earth, independent of mission control. Now you contrast it with automation. The dictionary definition is the automatically controlled operation of an apparatus, process, or system by mechanical or electronic devices that take the place of human labor. Or as we defined it within the roadmap, automation is the automatically controlled operation, so automatically controlled, keywords, of an apparatus, process, or system using a pre-planned set of instructions. So, it's like you program, well, I used to say VCR, nobody has a VCR anymore. You program your DVR, you program your whatever, set of instructions that just carries it on, following a recipe, following a script. That's automation. Autonomy is the ability to operate independently. It often involves things like making decisions, being goal-directed, being able to operate independent, and to make decisions without having everything precisely laid out and specified in just a script. There are a number of related terms. Those of you who are technologists in the room can certainly share with those who are not some of the words that we use, such as adjustable, line autonomy, mixed initiative, supervisory control, mixed agent teams, locus of control. All of these things are finer level words that have to do with how we think about autonomy. What is the extent of autonomy? Where is it important? How do we implement that? How do we make it so it's not a static thing, but perhaps a dynamic thing? I would contend that autonomy is important, and this is, I think, really the reason that we're here today, is thinking about when is it needed. Because clearly, if you can carry something out, if you can do a mission without autonomy and you be really successful and it's low cost and it's high probability of success, why would you add anything else to that? Well, I would point out that there are a lot of places that currently we cannot get to. There are things that we currently cannot do. For example, when the cadence of decision-making exceeds the communication constraints. If you're going to deep space and you're trying to observe a dynamic phenomena and you can't plan ahead of time where that phenomena is going to be or what measurement you're going to need to take, well, you need to make some decisions locally. You need to make it on board, which means the spacecraft has to be capable of independent action. Similarly, when decisions can be better made using rich onboard data compared to limited downlink data, we know that in deep space, we have a very limited ability to communicate everything that we can measure, everything that we can capture in terms of sensor data. And so maybe it's the case that we have to make those decisions using data on board a spacecraft and not just rely on downlinking, gigabytes or terabytes of data to Earth for us to then, worry about that. Anyway, there are a lot of considerations here. I think it's important to realize that the important factor is when can we not do things as sort of one motivation for looking at autonomy. There are other design questions too, which have to do with, once we decide to use autonomy, how do we factor that into our mission? How do we think about, the aspects that are allocated within mission control or not? How do we think about what goes on board and is performed either by humans, in the case of astronauts in deep space, or by spacecraft that are operating independent of Earth? How do we deal with the transition of authority? Who has control? Who has the ability to say, well, this is what we're doing right now, and why we're doing that? A lot of interesting design questions here. Now, one view of how autonomy fits into a system is this, which I credit to Jeremy Frank. It's a chart that shows lots of different aspects here. You clearly have, mission control or ground ops or air traffic control. You have crew, which could be pilots or astronauts. You have various forms of vehicles. It could be spacecraft, rovers, robots, landers, aircraft. And in the middle, you have all this stuff, all the things which allow these different parts of the system to communicate and different things which allow things to operate independently or perhaps autonomously. For example, if you're looking at ground control, here the primary locus of control, or really where the authority is for operating everything, resides with mission control. And they may use interfaces, various computers or devices in support of their work to plan and carry out activity. Crew control is very similar, except now you don't have ground involved, you just have people inside of a spacecraft, be that the space station or in future spacecraft, operating again with electronic support, and now they're all interacting with the vehicle directly. You can look at crewed vehicle autonomy, and this is an interesting situation where you have crew involved, but you may still also have ground mission control involved, but really the focus here is within the vehicle. I mean, that's really where the decisions are being made real time. Now, you can do this with the space station, but I think the more interesting thing for us right now, at least in terms of human exploration, is thinking about how future spacecraft can do this, and to delegate more authority to the spacecraft to make decisions. In any case, there are a number of different variables here. I won't go through all these here, just point out that you can look at different ways of considering where is the focus of control. You can look at whether or not that involves humans or if it's the spacecraft by itself. And this is just to point out and maybe hammer home the point that autonomy is a very complex thing. There are lots of different factors here to worry about. Let me briefly speak then about some of the lower level technologies. And as I said, if you're not familiar with these terms, there's certainly people in this room who are. And so, as you are discussing today in your breakout groups is interesting, feel free to ask questions. And in fact, I think that's an important part of today, is to really be asking questions of each other. In terms of technologies, autonomy involves many, many things. This is a chart that attempts to try to organize some set of the things that we think about as being supportive of autonomy. Everything from technology that supports collaboration and interaction. And again, remember, autonomy is a relative term, so you have to think about how you interact or how you operate relative to something else, which means you have to think about collaboration and interaction. Certainly, situation and self-awareness is an important part of any independent, any autonomous systems. Worrying about sensing, perception, estimating your current state, knowledge, looking at hazards, identifying important anomalies to deal with. Those are all part of the ability of a system to be situationally or self-aware. Reasoning and acting is something we've worried about for a long time. For all of our systems, even the ones that are just automatic, we clearly have to do a lot of planning. There's a lot of work in terms of motion planning, activity planning, task planning, just diagnosis and prognostics as part of the operation of any system. But if a system is going to function autonomously, it has to be able to do this all by itself. And of course, the pesky details of how you put it all together are things that clearly are important. One of the biggest challenges of any autonomous system is how do you build it in such a way that we are confident that we understand how it's going to function. What are the performance limits? What are the corner cases? What are the edge cases? Can we perform V&V on that system? Can we do test and evaluation? Very large, difficult, active areas of research and development today. Another way of thinking about autonomy is how these things fit together. For example, you can look at planning as something that folds into scheduling that then influences executive or task execution or diagnostics and state estimation. There's a multidimensional set of things going on here and lots of interconnectivity. Don't kid yourselves. Autonomy is not something that is just trivial. But why do we care about it? We care about it because it has the ability to let us do things that we can't do otherwise. Some of the core parts of this here, and I think that I keep picking on Jeremy, but this is one of the things that Jeremy does. Jeremy's group here at NASA Ames is called the Planning and Scheduling Group. So if you want to know about planning and scheduling, you can go bug Jeremy. Planning and scheduling is all about building plans by choosing activities to achieve goals. And that sounds straightforward. Oh, we can make plans. All of us make plans every day. But it can be very, very complex when you start factoring all kinds of different constraints and you start worrying about resources and you start worrying about ordering, and then you realize that, all these things are interconnected. So planning and scheduling technology is really focused on us being able to come up with an optimal, or at least maybe an executable plan, something that we can carry out. It's something that right now for a lot of our missions is done with a lot of human involvement. And I think that one of the core things, if we're looking at systems that can function more autonomously, those systems themselves have to be capable of planning and scheduling. Once you've built the plan, of course, you need to find a way of carrying the plan out. And you think, okay, I've got a great plan, perfect, everything's solved. Well, we all know that any plan does not survive contact with the real world. You have a perfect plan of how to drive from San Jose to San Francisco. You get in your car and then you get on the highway and you realize, I'm in the Bay Area. I should not be on the highway at 3 o'clock in the afternoon on 101 because there are other people here too. And so what happens is you have to figure out, how do you execute this? Maybe your plan has branching. And so you say, well, I shouldn't go up 101. I'm going to flip over to 280. Rush over there and find out, there's another traffic jam here. Now what I'm going to do, well, I'm going to pop up Waze because it must know more than I do. But basically the problem of executing a plan is still a complex thing. Beyond that, of course, then this whole issue about what happens when you run into faults or anomalies. You might be driving down the highway and your car breaks down. What happens? Well, I don't know, maybe you're going to get on your smartphone, you're going to call an Uber and think, well, it's a rental car, I can leave it on the side of the road. What could possibly happen to it? I won't be liable. But the point is here that you have to think about, how do you predict, how do you analyze, how do you take corrective action when there are potential faults? All these things are the lower level technologies that make up autonomous systems. It's important for us to understand, as I said, that autonomy is not a single thing, but it's a collection of things. And beyond that too, there's certainly supporting technologies that are important. A lot of our autonomy, in fact, probably most of our autonomy that we add onto our systems these days are provided through software, which means that we need things such as user interfaces to be able to understand what's going on. We have to integrate to the basic flight software that operate our spacecraft. We may need high-performance computing. In fact, one of the fundamental limitations today on Mars, if you're looking at the rovers, if you look, for example, at Curiosity, it is limited in a large sense of being autonomous because of the limited onboard computing power it has, both in terms of memory and just CPU speed. So adding more performance, higher performing computing may be one of the required and necessary things in order to carry out more autonomous operations. And then, of course, there are things such as learning. A lot of things that we care about of being autonomous means that we can operate independently. But operating independently means that you're capable of coping with changing circumstance. And the way of doing that may require adaptation, require learning. Where we are today is a place within NASA where we recognize that these technologies are important. We recognize that we want to mature these, to develop these further, and so that we can make these systems, make these missions more autonomous. And some of the work here is focused on developing new algorithms. There's certainly a need for being able to create systems that can deal with more complex situations or maybe larger scale. One of the problems we have right now is that some of these missions that we want to carry out require dealing with things that are orders of magnitude larger than we've ever done before in terms of like the number of data items, number of telemetry points, the size of our plans. Applying the technology is something that we may need to worry about not just as individual components or parts of operations, but for large-scale systems, the entire mission, the entire spacecraft. And again, as I said, having to deploy these on flight computing systems. There's a lot of research and development in all the technologies I talked about, certainly in terms of planning and scheduling, trying to look at performance improvements. The same thing is true in terms of task execution, trying to look at how we can make these executives more robust and be able to incorporate real-time simulation and deal with contingencies better. In terms of state estimation, a tremendous amount of work is being done right now in trying to figure out how to better do verification, validation of health systems, do more advanced fault detection that may involve high-fidelity physics-based modeling that operate in real time. And I want to point out that each part of NASA, whether it's human exploration, whether it's space technology, whether it's science, has some set of notion about where they'd like to go. Mike talked a lot about SMD and the future of technology development, the future of innovation. Other parts of NASA are thinking about this as well. This is a chart that comes from the Human Exploration Operations Mission Directorate looking at the roadmap for where autonomy can fall into. And that white line is where we are today. You can see that we have to move and develop these systems to allow crews to be more independent. For example, to do self-scheduling on board the vehicle instead of relying on planners on Earth that will generate plans and tell them, well, here's what you have to carry out today. HEO has taken a very long-term view here. Of course, part of that is driven by the fact that building up the capabilities that will allow crews to go beyond Earth orbit, whether that's in the Earth-Moon system or beyond, will take a very long time. And so along that path here, there's a long-term set of things that have to be developed. Let me just wrap up here and be happy to take questions for a few minutes by pointing out that autonomy is something that I firmly believe is required to enable and enhance future missions, particularly deep space exploration, whether it's human or robotic, that are more complex, especially in environments that are adaptive, dynamic, places where we really worry about engaging with the environment in ways that we can't just plan ahead of time. I want to point out also that autonomy can be accomplished in a lot of different ways or involve lots of different things, humans and robots together, spacecraft that are operating in ways that we are not currently operating them, and that it's important to understand that autonomy is something that cross-cuts all of NASA. So even though today we're talking and focused on autonomy for SMD missions, just want to remind you all that NASA as a whole cares a tremendous amount about autonomy, and it's something that I think is going to be essential and core to our future. And with that, I'm all done, and we have time for maybe 5 minutes of questions. Butler, you've got the box.
So I've actually been on both sides of the fence where I've been pushing for autonomy, and then I've been on the spacecraft side and saying, wait. So one of the things I want to emphasize is one of the barriers is how you test this stuff. Because autonomy, by definition, you're making complex decisions based on complex input, and so it's really hard to do the standard type of testing we do with flight software and predict what it's going to do. And so that's one of the challenges and barriers to entry into flight missions is really predicting what it's going to do in all situations, because it's honestly, it's easy to break a spacecraft. It's easy to make a stupid decision and break a spacecraft, and so you really need to know what you need to be able to predict what it's going to do. You need to be able to test it in a wide variety of situations.
Yeah, and I think just to respond to that, I think that is certainly one of the most difficult areas that we face if we're trying to make systems more autonomous. And it's not just spacecraft. I mean, you look at self-driving cars, for example. Here in the Bay Area, there are self-driving cars everywhere. And as I mentioned, you'll run into them every single day. If you just, even for me, I commute 10 minutes from home to here, and I run into at least 4 cars every single day. Some of that is really focused on trying to get a handle on how can we test those systems so that people will believe that they're good enough to use. Waymo, for those of you who are not familiar, Waymo used to be Google in terms of self-driving cars. They've driven something like 3 million miles autonomously over the past year. But the question is, do we believe that that's good enough testing? Do we believe that they've actually learned enough to say, oh yeah, we'll trust them. We'll take the driver out, and we'll just let the car go. And I don't believe that that's the case. There's still a big question of what's necessary to allow us to have confidence that we understand the system, even if we haven't perhaps tested it to all possible corner cases, which I think is one of the by far the biggest things if you're saying, well, I'm going to let a system do things beyond what I just pre-plan and carefully validate. Next question. Jeremy, you got the box.
Let me follow up on Butler's question. So Butler's right. We do have this fear factor about these autonomous systems that quote unquote behave in all these ways. I want to draw an analogy between sort of classic AI technologies like planning and scheduling and control theory. So we build controllers. We build continuous controllers, dynamic feedback controllers, and there's this notion of sort of a behavior space and a boundary. And we have some experience in testing those. And so for the technologists in the room, this is not an answer, but we have to ask ourselves, how do those continuous controllers get tested? What is it that we can learn about how those tests and testing methodologies are done, not only to develop better ways of testing, but also to explain to people, listen, here are these other technologies that people develop. You don't call them AI, but they're doing something similar. So if you have a difference in your trust between these two systems, maybe if you think about that, it can make you feel a little better about what it is that the AI technologies are doing.
Throw the box here.
You mentioned briefly about the impact of limited computing on your rover vehicle. How far have you gone in estimating computational requirements for some of these autonomous functions?
So I think that's certainly a difficult question to answer in a simple way. I mean, part of what different systems need to be more autonomous in terms of computing has a lot to do with the amount and volume of either data or the scale of the problem that they have to deal with. On the rovers on Mars today, for example, one of the barriers or one of the limitations of moving faster or doing more autonomously has to do with the amount of data that's being processed in terms of like image data. So for example, on Mars rovers, if they're going to drive autonomously, and there's a function called AutoNav, that requires processing of high-resolution stereo images, making correlations by processing large amounts of data. And that's a very, very slow thing. So in fact, you look at Curiosity today, in autonomous mode, it drives a lot slower than it can drive if it's driving blind or if it's driving in a scripted way. That's something that's being addressed to some extent in the design of Mars 2020, where there is specific computing that will be focused on processing images faster. So part of it has to do with the problem. If you're trying to do large-scale data processing, maybe you need a specialized processor to deal with processing large amounts of data. On the other hand, some of the problems that we're looking at have to do with the complexity, and maybe it's the scale of the problem. And instead of dealing with plans that are on the orders of tens or hundreds of steps, you're thinking about things of thousands or tens of thousands. And there, it might actually require a different kind of computing architecture to deal with that. Other questions?
For an autonomous conference, you should have an autonomous thing that just gets to the next person.
Hi, Anupa Bajwa at NASA Ames. So Butler, regarding your question on how we test these, it's hard. You don't want to break your spacecraft, but it's okay to break a simulator. So I propose that if we put in a lot more effort into our simulators, fold in the control loop capabilities into these simulators, places where you can inject failures, places where you can explain what's going on so that the human trusts the simulator. All these are possible things we can invest in. The other thing is there's an inherent capability of systems which says that if you design for optimizing in the center of your space, you are going to break at the edges. If you try to stay safe on the edges, you're not going to get optimal performance in the middle. Likewise, for false positives, false negatives, it's a balancing act. You can't have both. So as long as we understand that for autonomy, we should be able to design our simulators to take care of all these things. One last thing, all these systems are inherent loops, basically. And once we start training ourselves to think of systems as loops, and a classic example is a predator-prey loop. It's a self-balancing system. So in our autonomy, are there self-balancing loops or are there reinforcing loops? Once we start to understand that game, we can come up with archetypes that are inherent in these architectures and start playing to those strengths.
Great, thanks. I apologize, I know there are other questions, but we actually need to keep the schedule because we have so many things going on. You've got the box, all right. One last question.
Yay! All right. Thank you. So I work with closed loop systems and autonomy and scientists, and I bridge the gap between scientists and engineers. So the first two questions or comments and the aversion of scientists to autonomy is a very common problem for me. And what I find often is the biggest problem is that the development of these systems is completely closed. So nobody knows exactly what's going into the logic of programming autonomy. And so what kind of solution might you propose to open up the development of these systems to scientists, to flight, like aerospace practitioners, so that way the ghost in the machine, so to speak, like the bias that's being applied by the engineer, isn't just an engineering bias. So that way this autonomy has the combined experience of all these parties throughout the development process and through the testing process.
Great. I actually really thank you for that comment. I'm glad we let you grab the magic box because that's actually a perfect lead into our next talk.